Okay, quantum theory. Now that we have seen and understand that light, while it was classically considered a wave, also has particle natures. The energy of it is quantized, and we call a packet of the smallest size of energy that can come in a photon. Right? And now that we understand that actually the energies of the electrons in an atom are also quantized, right? We can't have just any old value. It's either E1 or E2 or E3, and we see those transitions. Um, and we get the sense that, gee, there's a difference between the microscopic world of electrons and photons and the macroscopic world where you and I live. Um, to further develop this, we have to go into a little bit of quantum theory, and that's what this section's about. See, like I said, in the macroscopic world where you and I are, energy is continuous. I can drive down the road at 1 mile an hour, 2 mile an hour, 2.5 mile an hour, 100 miles an hour, any number at all. A continuous variation is totally possible, and therefore my kinetic energy continuous. Whereas in the microscopic world, this quantization occurred, right? The energy of an atom, it can't be just anything. It's E1, E2, E3. And you can't go in the middle. Strange, right? Or light, it can't be any old energy at all. It actually comes as a quantized packet called a photon. Right? That's very unusual to us. We can't imagine saying, okay, I'm driving down the highway, but you're not allowed to go just any old speed you want because your kinetic energy is quantized, and you're going to have to go either 3 miles an hour or 17 or maybe 39, or it's like, what? No, I can go anything I want, because it's a very foreign idea to us in the macroscopic world. But yeah, in the microscopic, it's not that way. So in the macroscopic world, we either have a wave or we have a particle. You have a baseball or you have an ocean wave, but those are very two different things. In the microscopic world, we have this idea of a wave particle duality. An electron seems to be both. We think of it as a particle. It's got a charge. We can think about it as moving from one place to another, being given away, transferred in an ion, right? An ionic bond, that kind of a thing. And yet, it also behaves like a wave. And we can see that electrons actually can do like the double slit experiment, where you actually get this interference pattern of destructive and constructive interference, just like you would on a wave, not a particle. And so it behaves as both. It seems to have properties of both. And the same thing was true for photons of light. Sometimes they behave like a wave, other times like a particle. And so we have this duality, this dual nature at the microscopic world. So de Broglie came along and said, okay, well, if electrons, I should say, can have this dual nature, this wave-particle nature, why not matter? Can matter have it as well? And we already know the electrons sometimes act like a particle, act like a wave. Well, if they can have a dual nature as well, just like a photon can, then a natural question to ask is, what is its wavelength? Okay, well, now wait a second. An electron, we think of it as a little particle, and it's got a charge. But if it's got a dual nature, then it's also a wave, and I think it's very natural to say, what is its wavelength then? What is its lambda? So Bohr thought about this. He went through the theory behind it, and he came up with a really simple equation to predict the wavelength of a hunk of matter. And this is it right here. This is the de Broglie wavelength. Lambda equals h over mv. mv is momentum, and so sometimes you'll see it as h over p. P is used as momentum in physics. So h over mv. Now notice this is v, velocity. It's not nu, which is frequency. All right, so they look very similar, but that's a v. That's velocity. So if I know the mass of this particle and I know how fast it's moving, then I could plug it into this equation, and it would predict what the corresponding wavelength of that particle is, if you view it as being a wave, or if you're looking at its wave nature, its wave properties. Right? And here's the key thing about this then, when you put this all together, Bohr's steady states that we talked about before in the Bohr model, the steady states of the electrons having different energies, he wasn't sure exactly what that would look like. Well, it turns out that those steady states and those quantized levels of energy make perfect sense if you consider the electron to be oh, not just any old wave, but a circular standing wave. Right? Not a particle, but a wave, a standing wave that's going around that nucleus. And we can calculate the wavelength using de Broglie's equation, h over mv. All right, so what is a standing wave? Because it's coming together, we're kind of seeing what the picture is. What do we mean by a standing wave? Well, a standing wave is simply a wave that fits in a confined region. That's all. And so, for example, if you have a wave, and let's say it's tied down on the left side, it's tied down on the right side, then I could take that and it goes up and it goes back down. That would be a wave that fits in that space because it's tied down and it matches on both sides. Right? It doesn't miss it, if you will. Okay, that would be a standing wave, and I could take it. I can think of it as like pulling it down and letting it go and be up and down, and so that's what they're showing right here. Kind of this vibration up and down. That is a standing wave. That would be a half of a wavelength as it goes up and down there. If I went for a full wavelength, so it goes up into the positive areas, and then back down here into the negative areas, and then comes back and gets tied down on the right side. That's one full wavelength there. And so a standing wave can either be a half wavelength or a full wavelength if it's tied between two things, like a guitar string. Okay, those are the different waves and therefore frequencies as well that it could vibrate at. The third one down here, I've got 3 half waves. That's a standing wave that fits, and here's 4 half waves. In other words, 2 complete wavelengths that fit between those 2 tie downs. And if this thing is vibrating up and down, up and down, up and down, then there's these regions right here that are called nodes, and they're always equal to 0. Because as this part goes up, this part goes down, and they vibrate and they go back and forth, but it always goes right through that one little node. And there's going to be nodes, 3 of them here, when I had the full 2 wavelengths here. Now up here I drew in red a wave that does not fit. It would not be a good standing wave for this guitar, right? Or whatever this is, because here it's tied down on the left, but even it's a little bit longer, right? And so it's going down, it's getting longer, and it comes back here, and it's up here instead of meeting down here where it needs to be tied. This wave, it doesn't work. It does not work in that physical dimension, right? So it is not a good standing wave. And it would be, as we say, not allowed. It's not a solution. It doesn't work in that particular environment. All right, so if the electrons, right here we said electrons could be considered circular standing waves. So essentially we've got this region around an atom. If that's the nucleus right there in the middle, here's the region around it. And if it's a circular one, then it's a standing wave going up and down, but it's going in this circle. And of course, again, as it comes back around, it's got to meet correctly where it left off. And that would be a perfect standing wave. And only certain wavelengths would fit. Only certain waves would be allowed in that region. In this case, it would have to be a multiple of the circumference around there. And so n some multiple of the wavelength would equal 2 pi r, which is the circumference of that circle. Only those waves with multiples of those wavelengths, so n could equal 1, 2, 3, 4, would fit. And so we see that the waves are restricted by quantum numbers. And it would be 1, and it would be 2, and it would be 3, etc., etc. And so this idea that the wave has to fit in a region leads very naturally to the idea of quantization. And therefore, if only certain waves fit and only certain waves are allowed, then the energies associated with those certain waves are the only ones that are allowed as well. And all of a sudden, bam, we see this quantization of energy, which indeed we've witnessed before. Okay. The 2-slit experiment, I mentioned this, or I alluded to this before. Here's where electrons can indeed be shown to exhibit this wave behavior. It's not just a particle. You see, if a wave goes through a double slit like this is called the double slit experiment, right? Then on the back side of the slit, it's kind of like a new wave that's coming out. It's emerging. If you got the slit, it's emerging, and it comes out, and it spreads out as it goes forward. And so as this one goes to the right, you see the top one, it's spreading out, the bottom one's spreading out. And as these waves start colliding, well, if one is up at the same time the other one is up, then when they collide, the high and the high add to give you a doubly high wave. Or if they're both down at the same time, then those combine to give you a doubly low wave, a valley, if you will. Right? However, if one is up when the other one is down and they collide in that way, then it's kind of like +1 and -1. They cancel each other out and they give you 0. And so as these two waves from the double slits start to interfere with each other, you get constructive where they add together or destructive where they cancel each other out. And if you put a screen over here, right, so if I shine a flashlight here and the waves come off and the particles, you get this pattern of bright, dark, and that's a clear evidence of a wave has going through those two slits. Now, if I had just particles, or I showed a bunch of particles through there, well, particles don't add and subtract like that. If I did a particle, I would expect to just kind of see the image of those two slits. The ones that go straight through it would go through and hit the screen, right? The ones that did not go through the slit would, bam, be hit by the wall and they wouldn't make it. And so on the screen, I would expect actually just two lines, one for each slit. And here's the neat thing. When you actually shoot electrons at a double slit like that, what do you get? If you do it long enough anyway, you see exactly the same kind of light, dark pattern that you get with light, or that you'd get if it's a double slit with water waves or any kind of waves. This is evidence that the electrons are actually acting like waves. And so we've got this, again, this dual nature, particle wave duality down here. All right, so let's take a look at example 6.6 from the book. Let's scroll down here and find it. 6.6, it says, calculate the wavelength of a particle if an electron is traveling at 1 times 10 to the 7th meters per second. That's pretty fast, right? And it has this mass, 9.109 times 10 to the minus 28 grams. It says, what's its wavelength? So again, we have a particle, and we're going to interpret it as a wave, and we're asking what is the de Broglie wavelength of that particle. All right, so here's the velocity. I just recopied it here. And the mass, 9.109 times 10 to the minus 28 grams. This is part of the MKS system. MKS, let me just write that over here, meaning meters, kilogram, and seconds. All of the higher or compound units in the metrics, such as a joule for energy or a newton for force or a watt in an electric, all of these are built up off of simpler units, and those simplest units in this system are the meter, the kilogram, and the second. Right? So it's not actually the gram, it's the kilogram. And if I want to stay in the MKS system, which is so much easier if I do, then I want to make sure I'm in kilograms, which is why I've converted this grams to 9.109 times 10 to the minus 31 kilograms. Okay. Again, if you take a more theoretical or a physics class, or this would make a lot more sense to you. At this point, just remember go to kilograms if you're going to stay in the MKS system. There's also other systems like the CGS system, which stands for centimeter, gram, and second. And all of theirs are built up off those base units. Right? But we're going to stick with the MKS system, which is for the most part pretty straightforward. Like I said, you use meters, but you use seconds, but for mass you use kilogram. Alright, so accept it. Alright, so I've converted it to kilograms here. What is the wavelength? Well, again, de Broglie says that lambda equals h over momentum, so mass times velocity is on the bottom. I've got everything, I can plug that in. That would be 6.626 times 10 to the minus 34 joule seconds on the top. MKS units, right? A joule and a second. The mass, well, this electron weighs this, negative 31 kilograms. We already figured that out. And its velocity, yeah, they said that it was going at 1 times 10 to the 7th meters per second. Again, if that wasn't in meters per second, I'd have to convert and get it into those right units. But see, I'm using all of the correct MKS units, so I'm going to get them canceling correctly, and lambda, being a wavelength, will come out in meters this way. And all I have to do is go over here now on my calculator and plug those numbers in. So let's do that. 6.626 e minus 34, that's the top. Divide by the mass. The mass is 9.109 e minus 31. And then also divide by the velocity, which is 1e7 in this case. So that equals 72.7 times 10 to the minus 12 meters. Very, very tiny. That would be, well, 72. Remember, 10 to the minus 6 is micro, 10 to the minus 9 is nano, 10 to the minus 12 is pico, 10 to the minus 15 would be femto, and negative 18 is atto. So this could be interpreted as 72.7 picometers. That's not something you hear very often, right? But Negative 12. That is a very, very tiny wavelength. All right, and so this is an electron, and even when it's moving that fast, it's going to have a very small wavelength. So you've got to get these things going at the right speed and a very small mass in order to get a wavelength that's on the same order as themselves. If that happens, well, then you're going to see its wave nature. Let me go back up to de Broglie and make that point more here. De Broglie says the wavelength is h divided by mv. Now, as mass gets bigger, I'm dividing it, it's on the bottom, right? And so I'm dividing by a bigger number. That means lambda is going to become smaller. So you get bigger on the mass, the lambda, the wavelength, is going to become vanishingly small. You know, if I calculated the wavelength for a rock or for a baseball or something, it'd be so ridiculously small. I mean, no wonder I don't see it as a wave. I don't ever see its wave nature, because the wavelength is crazy, crazy small. I mean, even for an electron, like what we just measured there, with its mass, very small mass, its wavelength is still really, really tiny, 72 picometers. All right, tiny, tiny. Also, the velocity, how fast is this thing moving? The higher the velocity, the faster it's moving, the smaller the wavelength. And so again, what I would expect is when I get to these tiny, tiny particles, the wavelength, the de Broglie wavelength, when I calculate that, will be on the same order of magnitude size-wise as the particle itself. It'd be kind of like saying if I have something like me, say I'm 1.5 meters, if my de Broglie wavelength was also about 1.5 meters or in that range, well then I might look like a wave just as much as a particle. But if you stuck my velocity and my mass into it, yeah, the wavelength is so crazy small that, yeah, of course you never see it. All right. Next person that comes along here that we need to talk about is Heisenberg. Heisenberg knew a lot about wave mechanics and how to do that in the classical, and so here we got now the idea of taking particles like an electron and treating them like a wave, and so he knew how to do the calculations in waves, and he sat down and started figuring things out. He said, okay, if this is a particle and yet it's behaving like a wave, and you're going to try to measure this, what's that going to look like, right? What kind of limitations might there be on that? And he found a very interesting result. And we're not going to go through the math, but here's it. He said that the uncertainty, he called it delta x, so the kind of the change in x. Think about that as, well, final minus initial on x in this region. He said, that's my uncertainty. I don't know exactly where it is. I'll say it's between x final and x initial, this delta x, okay? So he said the size of the uncertainty of x times the uncertainty of that momentum in the x direction is always going to be greater than or equal to h bar over 2. In physics, h bar is the same thing as h divided by 2 pi. So h bar divided by 2 is the same thing as h over 4 pi, which is just a number, a constant. Kind of a really interesting result. So the uncertainty is multiplied to give you something always greater than h over 4 pi. Now, of course, h over 4 pi, that's a fairly small number. We know that h is negative 34, right? 10 to the minus 34. And so it's still a pretty small number in the typical units. But still, there's an uncertainty there. Also notice that because I'm multiplying these things together, if the uncertainty at x gets big, so if I'm saying I really don't know where the particle is, then the momentum uncertainty can actually go smaller. Again, as long as they're greater than or equal to h over 4 pi. So they can be kind of inversely related in some senses. One gets big, the other one kind of gets small, which has this interpretation then that I cannot know to some arbitrary position both a particle's position, x, and its momentum, or if you prefer speed, velocity, at the same time to some, again, arbitrary precision. There's always going to be some intrinsic uncertainty. Now again, we don't see this on the macroscopic world. Our particles are too big, the wavelengths are too small. We don't have to treat our particles as though they're waves, and so this actually is not noticed. Right? This only shows up in the microscopic world, and it's a direct consequence of the fact that these particles have a wave nature. If they didn't have a wave nature, you wouldn't have this uncertainty that Heisenberg discovered. And so this is called the Heisenberg uncertainty principle, and it's really easy to plug in. And if I want to talk about the uncertainty of x, This is just a big constant, it's a number, so I can very easily solve them for the uncertainty momentum, or vice versa. Right? So again, microscopic quantum world, quite a bit different, hard to kind of wrap your brain around, quite a bit different than the macroscopic world that you and I live in.